We now want to talk about photon energy, and we talked a little bit about this last week. Planck's quantum equation simply tells us the energy of a photon, and the energy of a photon is proportional to the frequency, as we've discussed previously. That's why an X-ray photon, since X-rays are high frequency, has more energy than a visible light photon, because visible light has a lower frequency. In order to use this equation, we need to know what h is. H is Planck's constant, and it's simply a constant, and the units that we use for that are electron volts times seconds. And energy in this formula is going to be in electron volts. We can also write Planck's equation in terms of the wavelength, and we can do that because we know that the speed of light is equal to the frequency times the wavelength. So therefore the frequency is equal to the speed of light divided by the wavelength. And you can imagine we can simply put in c over lambda for f in this formula, and when we do that we just get hc over lambda. So in other words, we've just replaced f with c over lambda. And we can use either this form or this form of Planck's quantum equation depending on what we've been given in the problem. Well, let's do an example. A diagnostic X-ray has an energy of 100 kiloelectron volts. What is the frequency of the radiation? Well, we know that the energy in electron volts is equal to Planck's constant times the frequency, and Planck's constant is 4.15 times 10 to the negative 15th electron volts. So in this example, we want to solve this equation for F. In other words, F is going to be the energy divided by Planck's constant, and we have the energy we needed in electron volts. We have it in kiloelectron volts, so that's 100 times 10 to the third electron volts, and we want to divide that by Planck's constant, which is 4.15 times 10 to the negative 15th. By the way, I missed a seconds up there. Electron volts times seconds. And by the way, you'll notice that the units we'll end up with will be 1 over seconds, and that's what a hertz is, cycles per second. If you work out this problem with a calculator, you will find that the frequency is 2.41 times 10 to the 19th hertz. And you'll notice that is a frequency of diagnostic X-rays if you look in your book. Let's try out a problem where we have to use the other form of Planck's quantum equation. So energy is equal to hc over lambda, and the problem says, what is the wavelength of a diagnostic X-ray that has an energy of 75 kiloelectron volts? So we're going to want to solve this for lambda. In other words, bring lambda up there and bring E down there. So lambda is equal to hc over E. And we have 4.15 times 10 to the negative 15th electron volt seconds times 3 times 10 to the 8th meters per second, which is the speed of light. And I'm going to divide that by the energy, which is 75 times 10 to the third electron volts. If you work out the math, you should get 1.66 times 10 to the negative 11th meters for the wavelength. The last thing we want to talk about in this section is matter and energy. And we started off way back at the beginning of the course talking about conservation of matter, which simply means that matter cannot be created or destroyed, and the law of conservation of energy, that energy can't be created or destroyed, that it's just transferred from one object to another. Well, it turns out that that's what classical physics thought, that those two laws were true, and they are, except there's one exception, and that is that energy can actually be transformed to matter, and matter can be transformed to energy. And that's what Einstein's famous equation E equals mc squared is all about. One of the things that you'll learn about later in your studies is something called pair production. And that's an example of energy being transformed to matter. Let me just tell you a little bit about what happens. In pair production, an X-ray comes in and interacts with an atom, and that the energy that's contained in the X-ray, since remember photons are pure energy, what happens is that disappears, and what comes in its place is an electron and a positron. And a positron is actually an antiparticle, it's an anti-electron. So in other words, energy in the form of a photon disappeared, and what came in its place were two particles. So energy is converted to matter. Now it turns out that when a positron interacts with an electron, because it's an antiparticle, they'll actually annihilate, and that matter will be turned back into energy in the form of a couple more photons. So energy can be transformed to matter. Matter can be transformed to energy. Another example of matter being transformed to energy is nuclear fission. That's what happens in both nuclear bombs as well as nuclear power plants, that we're changing mass or matter into energy. So let's see if we can do a couple basic problems with E equals mc squared. The first thing we want to figure out is what's the energy equivalence of a proton in joules and in electron volts. Now, the mass of a proton is 1.67 times 10 to the negative 27th kilograms. And what we're really asking here then is, how much energy, if I could take a proton and convert that mass entirely to energy, how much energy would it be? Well, that's what E equals mc squared allows us to calculate. The one thing that you have to be careful of here is that the energy here has to be in joules, and the mass in kilograms, and then C has to be in meters per second. Okay, so to figure out how much energy there is in that amount of mass, the mass of a proton, we just plug into E equals mc squared. So 1.67 times 10 to the negative 27th kilograms times the speed of light, 3 times 10 to the 8th meters per second squared. And if you do that math, you'll get 1.5 times 10 to the negative 10th joules. So that doesn't sound like a lot of energy, but a proton is a very small amount of mass. So just a little bit of mass is equivalent to a lot of energy. To answer the second part of this question, what would that be in electron volts? We just have to convert from joules to electron volts. The conversion factor is this: 6.24 times 10 to the 18th electron volts is equal to 1 joule. And so remember how we do conversions. I want to convert 1.5 times 10 to the negative 10th joules, and I want to convert that to electron volts. So I want to take electron volts and divide that by joules. So I want to set up my conversion factor that way. You can see joules cancels with joules, and if you do the math, you should get 9.38 times 10 to the 8th electron volts. Here's another problem. What's the mass equivalence of a 50 kilo electron volt X-ray photon? So again, energy is equal to mass times the speed of light squared. And the first thing we're going to have to do here is convert kilo electron volts to joules. So we have 50 times 10 to the third electron volts. And in this case, I'm going to use the conversion factor from the previous slide, but I've got to put it upside down because I want to end up with joules. So 6.24 times 10 to the 18th goes on the bottom, and that's electron volts. And I can see now electron volts cancels with electron volts. And basically I just take 50 times 10 to the third and divide by 6.24 times 10 to the 18th. And I get 8.01 times 10 to the minus 15th joules. Once I've got that, now I can solve E equals mc squared for mass. Mass is equal to energy in joules divided by the speed of light squared. So I have 8.01 times 10 to the negative 15th joules, and I divide that by 3 times 10 to the 8th meters per second, and I have to remember to square that. And if you work that out, you will get 8.9 times 10 to the negative 32 kilograms. And really what that shows you is that the energy of an X-ray photon, it's equivalent to a very, very, very small amount of mass, because a small amount of mass gives you a fair amount of energy.